Okay, we're going to walk through the practice 6 activity, which does k-means clustering here. Um, so again, this is done in a Jupyter notebook that you can run in Colab or in Jupyter on your desktop, and you can download it either way. Um, Like the last one, this is broken up into sections. Section 0, you have to run. It sets up all of our libraries and imports. So you always have to run that. And we'll be using two different data sets, the iris flower data set again, and then we're going to introduce a new data set from the St. Scholastica's biology department on microbes. So let's look at the iris one first. So in the iris data set, we read it in again as before and set it up. And remember, this has 4 different features for each flower. There's also a labeled data set, so we have the species here. Now, generally with unsupervised learning, you don't have this label here, but we'll just use it initially just to kind of get a comparison and idea of how this data is set up. So we will do the clustering without that, without training it on that, and then we'll just compare the clusters found with these actual species. We set up the data set again, and again, we will use an X iris and a Y iris, but again, we won't use this Y iris, the labels, for any of our training for k-means. It's unsupervised, so we don't need the labels for this. As before, we're going to do some scaling of this data. So we're going to set up a scaler and run the data for that. So our iris data is going to be called iris transform after this. Now we could also run principal component analysis to reduce the number of features, but there's only 4 features here, so we really don't need to do that. So we'll just do a scaling of the data here and use that. Now here's where we're actually doing the k-means, and this is where we specify the cluster size, and you'll have to come back here and change this. So this is cluster size of 3, and we can change this. If we wanted 10 clusters, you could change this to 10 here. We create a k-means object here, and then we fit that to the data, our transformed iris data from up here where we scaled it. And again, this is just the data here where it doesn't include the species, so we don't get it's unsupervised here. And it generates some labels for the clusters. And this is where we're going to plot the data. So we're going to plot the transform data, and then we're going to colorize it either with the labels given from our clusters, or again, we're going to return to the species and look at the species that are actually given. Now, in a perfect world, the clusters should match the species. And so here's with 3 clusters here. And you can kind of see this. This is the actual flower species. So these were all one species of flower here, and they're all generally in one cluster. So that worked pretty well. But again, these 2 clusters, the green and the gray cluster here, are kind of intermixed in this diagram and a little harder to tell. And so you can look here and you can see some values here. Now, in these diagrams, also some of the dots, some of the flowers overlap, and so there are some dots that are darker, meaning that there are multiple flowers at that location here. But again, we can see things like the color. It's a little hard to tell with the coloring, but again, like these 3 are all in the same species, but in the are not all in the same species, I should say, because this is a graph by species. Some are green and some are gray, but in the clustering, these were all put in the same clusters. Here. It does do some nice things like these are all in the same species and they're clustered together also. So it's kind of hard to tell, but you can see a little bit, at least visually, how that works. Now, some other better ways of analyzing these clusters is to look at a mapping. So this is each of the species, and this is what clusters they were put in. And so this species of flower were all put in cluster 0, and nothing else was put in cluster 0. And so again, this maps to this cluster that mapped out pretty well. But with the other 2 clusters here, this species was put, 47 were put in this cluster, cluster 1, and 3 were put in cluster 2. This last species was the most confusing. 14 were placed in cluster 1 and 36 were placed in cluster 2. So again, since we do know the actual results, we can do this comparison here and kind of see that it tried to put all the clusters in the right spots, but it didn't succeed entirely with that. Now, one question you could, so a couple things you have to do is analyze this and try this with different numbers of clusters. So again, you can go up here and try this with like 4 clusters or 2 clusters. So I can run this. I have to go back. I haven't run this also. I've got to go back up the top and make sure I run this first one up there and then import the data, set up the data, min-max it, and now I can go back here and do the clustering and display the clusters. So this is with, what did I set it to? 4 clusters here. So this is my cluster. So we have 1, 2, one kind of interval, and 3 and 4 here. And you can look with, let's run this again. With the 4 clusters, again, all of one iris was in one cluster, but the other ones were broken up. So this cluster had some of this flower and some of this species, but this cluster had all of this species in it. But not all. There were all other flowers of that species which were in other clusters here. So again, you can do some analysis by looking at this graph, running this with a couple different values of k, and seeing what might be a good number of k here. We know there are 3 species of flowers, so you would assume that 3 clusters would be the best choice here, but it might not be. Now we're going to look at elbow analysis. If you remember from the overview of the class, this is the elbow analysis, and what we want to do is find the amount of clusters where the distance between flowers in a cluster is small, but the number of clusters is also rather small. So again, when all the clusters are, when we just have one cluster and all the flowers are together, they are spread out a lot. When we have 8 different clusters, the flowers in each cluster are relatively close to each other because of the small clusters. But again, going from 8 to 10 to 12 clusters doesn't make them much closer together. So again, you want to be watching where this the elbow curves and look at cluster values around there. So generally around 2 or 3 or 4, maybe 5 values here. So we have some questions you can answer about that cluster now, that elbow and stuff like that. And one of the questions is, are there really 3 species here? Would you think there might be only 2 species? Maybe there are 4 species, some subspecies here of this. The naming of these species was done before we had DNA analysis and that sort of stuff. So sometimes the way we label species is not entirely accurate that fits the actual data. So that. Okay, and then we get into silhouette analysis. This big chunk of code comes from sklearn and does silhouette analysis, and it does it for 2, 3, 4, 5, and 6 clusters, and we can see that. So with now I can scroll up and down here. I'm going to scroll up within this. There. So again, this was with only 2 clusters. And again, I don't want these to go negative, and I want them as high as possible. And so this is a nice clear cluster. This is our one uniform cluster, good, and almost all the values are above 0.5 here. This is a more spread out cluster. You can see it's more spread out. It drops down more here, and in fact, some of the points don't fit that cluster that well. For this, there's some outliers here and here, but none of them drop to negative, so that's good. Now here's with 3 clusters here, and again we have this cluster which is very clear, and these aren't so much. And again, you can look at that for 4 clusters, and again we're beginning to see some negative values here, 5 clusters or 6 clusters, and then your job is to answer this and say what do you think are a good number of clusters based on these graphs, and describe why. And again, we generally don't want the clusters distances to go to negative values here. Those are generally mean that the clusters aren't very well defined here, and we want them as high as possible here. These red lines show the average of all the clusters, and this one where the red line is above this one is better. It means that all the lines average above that for this. So you can kind of look through that and give some analysis to how many clusters of irises you think there actually are for that. So that wraps up our iris data. Then we're going to basically do the same thing with some microorganism data. Um, our biology faculty have been collecting data at a couple remote sites, and this is data from one of these remote sites. I believe this is from Hawaii. And they collected samples from 100 different locations in Hawaii, and they were all labeled AK01 through AK100 here. And at each site, they did DNA testing of the samples and tracked down what DNA microorganisms they found there. Now, there are actually over 15,000 different organisms they found, but that was almost too big of a data set for this class sample. So I dropped it down to the 1,000 most common organisms that we have, but we still have, so for every location we have 1,000 different features, and that is the number of data points or number of organisms of each type in our sample here. And I've actually done some work so that the number, rather than a hard code number like 1,400, is actually just a decimal number between 0 and 5, and this uses what's called a logarithmic scale to try to compress the data a little better. So here we're opening up this, we're importing this data. So this match is similar to the iris stuff. Here's a quick view of our data. So here's our different locations, AK03. This is from lava rock, numbered 1969. It was collected on this date. This is the time, the temperature, humidity. So this is some information collected about that sample, including the altitude it was at, how high up the mountain it was at. And then we count all these organisms, and again we have these numbers that are a count of how many of those organisms. So there are going to be lots, so, we might not find any of this organism here or this organism, but we might find more of this organism or this microbe here. So this is the count of each one of these OTUs is a different microbe, and this is how a measure of how many of those we found at that site. So again, we do some setup with the data here. We want to just look at this microbe data. We're going to take these attributes like height and stuff and move that off. So this breaks the data up into attributes data frame, and then the microbe data frame is just the 1,000 values going off to the for each 1,000 values here. We do some min-max scaling on that, but here's where it's important. Now we've got 1,000 features here, so for each data set there is actually 1,000 different features. We start here, and this dot 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 just shows that there's a lot of missed data here. So we have 1,000 different columns here in our data set. So we're going to do principal component analysis and reduce that 1,000 data set down to 10 features. So go from 1,000 features to 10 principal components and set that up. So now we have our microbe transform data that we'll be using for our clustering. So here we're using that, and we're setting up our clustering with 5 clusters. And again, you can try and data. And again, we don't know. These are different locations, and it's really unclear, and there's no clear definition for how many different classifications or clusters of data of locations there are. And the question is that as you go up a mountain at a certain elevation, do you see a change in what microorganisms are there? And if you go up, are there points where the locations are kind of clustered together, that within this range of humidity values, elevation values, temperature values, you'll see this type of organisms, and then at another elevation or another temperature you'll see a different set of organisms, and we're not really clear. That's one of the reasons they're collecting this data. And so your job is really to try to figure out how many clusters this data is broken up to, and we'll actually be sharing this with the researchers at St. Scholastica with this data. So here's a plot of the data again. Let's do this k-means cluster. Oh, yeah, we haven't done this either. Okay, sorry, talking too much. They just run these things. And then the graph. And again, these are our 100 data points, and some of them are overlapping because they went back and collected the same sample at different times and temperatures, times of the day at different sites. But these are 100 things, and then the question is how many different clusters do you see in this data? And then this is just showing the two principal components, and so that sometimes doesn't show the true nature of the data. So again, your write-up is to try to figure out how many clusters the data should be broken into. We have 100 locations. How should they be broken up? So again, you can recluster this. You can say, I want to try 3 clusters, or I want to try 20 clusters, and it will try to break your data up into clusters here. And you can write up about that. You can also look at the elbow plot here, and remember the elbow plot shows the number of clusters. So with one cluster, all the data is pretty spread out. With 14 clusters, all the data is, each cluster is relatively small, and all the data points there in each cluster are pretty close together. But in between here, you want to look along this elbow at what are some better cluster values here. So again, you want to be choosing cluster values along the bend in the elbow here. So again, you can talk about that, and your write-up should be how many clusters you think we should be breaking this set of data set in. And again, we do not have a known answer for this, so this would be interesting for you to determine. Likewise, we can do silhouette analysis of this data and generate these graphs with different numbers of clusters, and right now it's using between 2 and 6 clusters, but again, you can add more or remove points there if you want. But so it shows with 2 clusters, and again, we kind of want to watch these negative values if possible here. 3 clusters here, 4 clusters, 5 clusters, 6 clusters. So and again, we want, so you can kind of see this is a bad cluster. It's fairly low here, starting at 0.3 and going down, and then there's a fair number of negative values. So this is not a very good cluster for us, not a very natural cluster. Now, another thing we have to watch when we do this is when we run this again, we'll get different results. And so in particular, and I forgot to mention this up in the IRIS database, when you run the IRIS data set, we want you to run it more than once. So we want you to run it and then replicate the value. So you can run it with 3 clusters once, and then you can run it with 3 clusters again. So this time I ran it, I had all 50 of this one, and then this was broken up by 3 and 47. But again, if I run this again, I might get slightly different clusters. So I'm just going to do that again, and this again. And now I'll have different clusters. Before all this, the clusters were all in this cluster, and it'll randomly assign these centroids, these central locations here. But again, you'll get some different values, but again, often the flowers will break up into very similar results. So your idea, one of your jobs here is to replicate the results and see if you get drastically different results. Now, in our microbe data, we'll see that again here. In fact, this value here where we might have a very bad cluster one time, if we run this again, we may not have that bad a cluster. So again, we can go back up here and do our k-means clustering again and see how this works. Oops, I'm up in the IRIS data. Sorry, I should be down here. Let's get down into this next data set. So again, when we're working with these microbes, the data is read in fine. But again, when we do the k-means analysis, you can replicate that and see how it looks, and it will change for that. Also, when you do these graphs, sometimes they will change because it'll pick different clusters each time. Now, often they're similar because of this, but we'll see some of the same results on some same bad clusters here. But sometimes, again, when you randomly select these, you'll get slightly different results. So that's something to be aware of. Okay, and the last type is then to look at those silhouette analysis and to write up what do you really recommend for the number of clusters, how many different locations, how would you break up the locations, and in how many points. So that wraps up this practice exercise. Hope you enjoy it.